So now in this section, we're going to focus pretty much on cell potentials, looking at them from various different ways. There's going to be a lot of repetition as we go from one question to the next, so I'm not necessarily going to have too much redundancy in what one discusses. So starting off with a list of half equations and the associated potential right there. Notice all of these are reduction half equations because the electrons are on the left. So this is a sphere reaction in which F2 is gaining electrons, Pb2 plus is gaining electrons, and so forth. And so we list the potential associated with it as being a reduction potential. So if I looked at this, I would say fluorine really wants to be reduced. Calcium 2 plus really doesn't want to be reduced. Negative reduction potential, not wanting to be reduced. Nice big positive reduction potential for really wants to be reduced. But now we look at the question and we are asked to select the best reducing agent of those provided. And now if something is a reducing agent, it itself is oxidized. So therefore what we want is, we don't want anything to do with the reduction potentials, we want to be looking at the oxidation potentials. And something we're going to do so many times during the rest of this worksheet is we're going to go from reduction potentials to oxidation potentials. The way we do that is we take the equations and we flip them. And then when we flip the equations, we also change the sign. So therefore you can see here, this first equation was F2 plus 2 electrons goes to 2F minus. Now we have 2F minus going to F2 plus 2 electrons. And because we flipped the equation, we change the sign. So going from reduction to oxidation. Now we wanted the best reducing agent, which is the one that most wants to be oxidized. So the one that has the most positive oxidation potential. So looking at all of these, obviously calcium. So calcium is the best reducing agent. F2 would actually be the best oxidizing agent. Same kind of question, which is the strongest oxidizing agent present associated with the following half equations. Well, if we want the strongest oxidizing agent, that means whatever we're looking at is reduced. And so we want the one that's got the highest reduction potential. However, when we look at these equations that I've given you, hopefully something will leap out at you as being a little bit strange, and that is that the electrons are on the wrong side. I have given you the way that we used to see tables back before I was born, these as oxidation potentials. So what we got to do here is go from the oxidation potential to the reduction potential. So same kind of idea. There's our oxidation potentials as written there. Let us flip them around, so now they represent reductions, and when we flip the equation we obviously have to do something with the potentials. We reverse the potentials, change the sign of the potentials, so therefore the strontium, that was a strontium going to strontium 2 plus, oxidized with a nice big positive potential. Now strontium 2 plus being reduced to strontium is a nice negative potential. So now to actually answer the question, which is the strongest oxidizing agent, which one most wants to be reduced, and the answer is going to be CO2 plus because it has the most positive, or in this case the least negative reduction potential. So CO2 plus is the answer there. Question 23 and question 24 are essentially similar questions that are just multiples of what we just talked about. So let's look at what we got here. We've got some standard electrode potentials, reductions, minus 0.44, minus 1.66, plus 0.77, and minus 1.18. So which following statements are correct? Fe2 plus is a stronger oxidizing agent. Well, if it's an oxidizing agent, we're talking about reduction potentials. And so what we're effectively saying is the reduction potential of Fe2 plus greater than the reduction potential of Mn2 plus, which would mean that Fe2 plus wants to be reduced more than Mn2 plus wants to be reduced. So let's go find them here. Fe2 plus minus 0.44, Mn2 plus minus 1.18. So that is a true situation. Now we're going to compare Fe3 plus and Fe2 plus. Fe3 plus is a stronger oxidizing agent, and Fe2 plus, well, that would require that the reduction potential of Fe3 plus is greater than the reduction potential of Fe2 plus. Here's Fe3 plus 0.77, here's Fe2 plus minus 0.44, so indeed 0.77 better than minus 0.44, so that one is also true. And then finally, Al3+ is a weaker oxidizing agent than Mn2+. In other words, the Al3+ is going to be less than the Mn2+ in terms of the reduction potentials. Find them here, Al minus 1.66, Mn2+ minus 1.88. So again, minus 1.66 less than minus 1.18 volts. So that is true. So this particular question, all of these are correct. Question 24, same idea, giving you a bunch of standard electrode potentials that you can see are all reductions. But now when we look at the possible things, we're talking about reducing agents. So therefore, we don't really care about the reduction potentials. We would love to have the oxidation potentials. So again, we flip the equations. So now instead of it being Fe2+ going to Fe, it's Fe going to Fe2+. And when we flip the equation, we change the sign. So here are the oxidation potentials, which are of course associated with the ability of a species to act as a reducing agent. So let's ask that in the same way that we did before. Here's Mn and Fe. So Mn plus 1.88, Fe plus 0.44. So Mn has a bigger oxidation potential than iron, so therefore it is not a weaker reducing agent. Now let's have a look at Fe2+ versus Fe. There's the Fe2+ being oxidized. There's the Fe being oxidized to the Fe2+. And so what we see here is that the Fe2+ minus 0.77, the Fe plus 0.44. So therefore the Fe is a better reducing agent because it has a bigger oxidation potential than Fe2+. So again, this statement false. And now finally comparing aluminium and magnesium. Aluminium plus 1.66, very good reducing agent because aluminium really wants to be oxidized. Mn, also a very good reducing agent because Mn really wants to be oxidized, plus 1.88. However, the aluminium is bigger than the Mn, so therefore aluminium is actually a stronger reducing agent than Mn. Using the standard reduction potentials given, which metal will reduce Mn3+ to 2+, we'll look at that reduction potential, 1.51. Mn3+ really wants to be reduced, but will not reduce Ni2+ to Ni. So Ni2+ has a reduction potential of minus 0.23. So it's going to be harder to reduce Ni2+. Pretty much anything will allow Mn3+ to be reduced with that huge big reduction potential. So what we're essentially saying is we want something that has an oxidation potential, because it's got to do a reduction, so it will need an oxidation potential, that is going to not be big enough to reduce this one. So we have to have it an oxidation potential less than 0.23 volts. Now, of course, if it's a positive one, it will still reduce the Mn3+ to Mn2+, because that's plus 1.51 volts. Indeed, the only things that will not reduce Mn3+ to Mn2+ would be those with oxidation potentials less than minus 1.51. But this nickel one here, we need to put a little bit of work in to reduce the nickel because it's got negative 0.3. So we would have to have at least positive 0.23 to reduce the nickel. So what we're looking for here is something that has an oxidation potential not enough to do that. Oxidation potential less than plus 0.23 volts. Looking at what I've given you here, there are a bunch of reduction potentials. We want oxidation potentials. Flip the equation, change the sign. So what you see is that all of these want to be oxidized. So all of them will have the capacity to do a certain amount of reducing. However, the lead can only reduce things up to a tune of giving it plus 0.13. Iron better, and zinc, of course, are very good reducing agent because it really wants to be oxidized. What we're looking for here though is the one that has less than 0.23 volts, and so that's the lead. So all three of these quite happily will reduce Mn3+ to Mn2+, but only the iron and the tin will be able to reduce Ni2+ because their oxidation potentials are big enough to overcome the minus 0.23. Poor little lead is not. So now we actually take the idea that I sort of introduced in the last one, and that's the idea of taking reduction and oxidations together to make a full redox equation and applying that to get cell potentials. So calculate E cell for the reaction 10 Fe3 plus I2 goes to 2 IO3 minus plus 10 Fe2 plus, and I give you these reduction potentials. So looking at the equation, I need to break it down into what is reduced and what is oxidized. I do that using oxidation numbers. I'm not going to dwell on these. We've dwelt on those far too much. But the reduction is the iron that goes from 3 plus to 2 plus. The oxidation is the iodine that goes to 2IO3 minus. Now, in terms of the reduction potentials and the oxidation potential needed for this, well, when we reduce 1 Fe3 plus, it's 0.77. How about when we reduce 10 Fe3 plus? And the answer is it's still 0.77. You don't worry about the coefficients associated with these particular half equations for the potential. All you care about is what is the potential. So the reduction potential here, because iron is reduced, is 0.77. The oxidation potential, well, when we reduce IO3 minus, it's plus 1.10 volts. However, here we're oxidizing iodine to make IO3 minus. So we flip the equation, change the sign. So it's minus 1.1 volts. Put both of those together. So 0.77 minus 1.10, and the cell potential minus 0.33 volts. So unknown metal in its salt combined with this half cell. Ag plus plus E goes to Ag and given the reduction potential. So what they're saying is the reduction is the Ag plus going to Ag. So the oxidation is M going to its M2 plus. Okay, so for the silver, we know the reduction potential is 0.8. We don't know, however, the oxidation potential for this unknown metal M. What we do know, however, is that when we put those together, the overall E cell is plus 1.36 volts. Again, notice, no need to balance anything. It doesn't matter that this is 1 electron and this is 2 electrons. All we care about are the potentials. So anyway, putting these together, 1.36 volts is going to be 0.8 plus X. Thus, X is 0.56 volts. So in other words, the oxidation potential to go from M to M2 plus is 0.56 volts. But that is, of course, an oxidation potential. We were asked for the reduction potential for M2 plus going to M. So that's the reverse one, which have the therefore there is minus 0.56 volts.